Hello, I'm Carrie Hulak, Social Media Manager for Berkeley Earth, an independent nonprofit organization focused on global temperature and air pollution data science. 2020 has been a record-setting year for climate change, with many months being the warmest since record-keeping began. We also saw a historically devastating fire season on the west coast of the US and more severe hurricanes as well. Today, Berkeley Earth lead scientist Robert Rohde and climate scientist Zeke Hausfather will spend a few minutes putting the trends into perspective. Welcome, Robert and Zeke. Thanks for joining me today.
Thanks. It's great to be here.
Let's start with how 2020 is ending up when it comes to global warming. In your recent temperature update, Robert, you reported that October is the 5th warmest since record keeping began, and that 2020 has an 80% chance of being the 2nd warmest year on record. Why don't you start off with explaining the trends here?
Yes, so 2020 has been running very close to 2016 for being the warmest year overall. And in fact, last September, it was the warmest September on record. And there have been several other months that have looked like that. October was a little bit cooler, not a lot cooler. It's still one of the warmest Octobers on record, but only the 5th warmest. And in fact, of all the months so far this year, it's the first one to be ranked so far down as 5th, whereas most have been ranked 1, 2, 3, or 4. And what we've seen happening is that La Nina, which is a pattern of cool ocean waters developing in the Pacific, has come in and pushed things down a bit from September. And we expect the La Nina to continue to develop going through the end of the year. And given that condition, it seems more likely than not, we will end up finishing the year a little bit cooler than 2016. Though it'll be pretty close, and it still remains to be seen how things end up.
Yeah, in fact, to add to that a little bit, it's close enough to 2016 that we'd probably expect at least one of the 6 different groups that report surface temperatures to probably have 2020 as the warmest year on record. We'll see, but it's definitely a toss-up at this point. And we'll know a lot more once we get November temperatures in, which at least so far in reanalysis products have been decidedly on the warm side. But we'll see what they look like in the surface temperature products.
Why is there a difference with the different organizations in how they end up with some of their numbers?
Go ahead.
Zeke, go ahead.
So there's a number of different methodological choices that the different groups around the world that reconstruct surface temperatures make that can affect the results. One is what data they include. So Berkeley Earth, for example, includes a lot more land temperature stations than groups like the Hadley Center in the UK. Another is the ocean temperature series they include. So we base our record on the Hadley SST3 series. NASA and NOAA, for example, who produce surface temperature records, base theirs off NOAA's ERSST sea surface temperature record. And there's some differences between those two and how they correct for changes in instrumentation and fill in gaps and other factors. And then finally, there's how different temperature records deal with the Arctic, where there's relatively sparser coverage of observations. Some groups leave large parts of the Arctic out of their analysis, in part due to an artifact of the way that they, reconstruct their spatial fields through gridding. Others, like Berkeley Earth and NASA, and Coughton and Way, use various statistical approaches to fill in the gaps in the Arctic between observations. And so those that tend to fill in the gaps in the Arctic show a bit more warming in recent years than surface temperature records that don't, in part because the Arctic has been warming much faster than the rest of the planet.
And that leads me actually to one of the next questions. Maybe Robert can start with this one. And you've noted some unusual activity with sea ice in the Arctic. So tell us about that and how that can cause warmer air temperatures.
Yeah. So one of the most remarkable features about this year has been the warmth across Siberia in Asia, which is more than 4 degrees above normal. And is setting a record far above any previous year. And that warmth in Siberia and across Asia has also spilled over into the Arctic Ocean. at the northern side of Asia. Back in the early part of the year, what we were seeing was unusually warm weather patterns in the spring and early summer were causing early melting of sea ice, exposing large areas of open water, which since developed into one of the most extensive periods of open seaways through the Arctic that we've ever observed. More than 110 days of open ocean through the Arctic along the Siberian coast. Now, as the year progressed, the causality flips a little bit, and you start having all that open water being the reason why things are so hot around the Arctic Ocean and Siberia. So, it's heated up during the summer, and it takes longer to cool down. It has now started to freeze over, but it did so considerably later in the season than it normally would. And all these the warm weather in the start of the year and the open sea ice in the summer have made for a very warm Arctic this year, as well as a very warm Asia. And that's contributed to overall the second lowest sea ice extent, but also one of the longest periods of open seawater in the Arctic Ocean.
Yeah, and if I can add briefly to that, when we talk about the effect of sea ice loss on temperatures in the Arctic, we're really dealing with two different factors. One, which is sort of a real factor, and one which is a bit of an accounting factor. The real factor is that when sea ice melts, it exposes, darker colored water below. That darker water absorbs more of the sun's incoming solar radiation and heats up more. It's what's called an albedo feedback. The second, which is a little more technical, is that the way that we generally measure surface temperatures is with air temperature over land and sea surface temperature over the ocean. And it turns out in that calculus, ice is treated as land. And so the air over ice can get a lot colder than the surface of the ocean itself, which is kind of limited by the freezing point. And so when you have a switch from a surface that is classified as air because it's over sea ice to a surface that's classified as water, sea surface temperature, you often have a bit of a jump up in temperatures because you go from below 0 to 0.
Okay, thank you. So as scientists, what concerns you most about this longer period of open water in the Arctic? I mean, just from a human, animal, do you go into that at all with your work, or just what disturbs you about that, or?
I mean, it's such a rapid change, I think, is what really catches my attention. That we've gone from 30 years ago when it was normal to have no periods of open sea ice in the Arctic. Essentially, the Arctic was closed to shipping year round, unless you had a sophisticated icebreaker. And now we've transitioned to a very different regime where there are substantial periods of open water, which is going to affect the ecology. It's going to affect the people living there. It certainly affects weather patterns around the Arctic as well. And it's a very rapid transition, which is part of the what we refer to as Arctic amplification. That there are feedbacks in the Arctic, such as the albedo changes, that are causing the Arctic to warm and change much more rapidly than the average.
Zeke, do you have anything to add to that?
Robert covered it pretty well. I mean, neither of us are ecologists, but obviously there are a lot of Arctic ecosystems that are under incredible stress due to rapid changes there, and a lot of human systems as well. We've seen a big oil spill this summer in Siberia when the permafrost anchoring a oil production facility thawed, and there was some collapse. We've seen a lot of roads collapsing in places like Alaska. And so, any part of the world that's changing that quickly is going to see some sizable impacts.
So Zeke, my last question kind of ties in following that up. I know you're also director, in addition to your work at Berkeley Earth, you're also director of climate and energy for the Breakthrough Institute. Is there anything you're working on that you're kind of excited about as far as studying solutions to climate change, maybe when it comes to innovations in clean energy or other projects to mention?
Definitely. Two sort of come to mind that I can talk about briefly. One is we're working a project around industrial inputs to decarbonization. The idea behind that is if we're going to rapidly change our global energy system to move away from fossil fuels, it's going to require a lot of materials to do that. You know, concrete and steel to build wind turbines, rare earth materials that go into electric vehicles, solar panels, wind turbine nacelles, a lot of concrete and steel that go into nuclear plants. You know, all of these things involve a lot of energy to produce. And it turns out that it's a lot easier to decarbonize your electricity sector to, you know, build nuclear plants or wind turbines or solar panels than to decarbonize, say, steel making or cement making, where you need very, very high levels of heat. And we generally don't have as good alternatives today, at least, to cost effectively produce very high levels of heat for those sort of processes besides using fossil fuels. And so what we're looking at is, you know, in a world where we really try to meet a 1.5 or 2 degree target in terms of the speed of our energy transition, both how much materials of different sorts are required for that transition, you know, what are the potential bottlenecks there, and, you know, what is all of the energy and emissions associated with producing those materials, given that the carbon intensity of production is generally going to lag behind the rest of the economy and decarbonization. So how much of our remaining carbon budget gets taken up just by building the stuff to decarbonize? And so that project will be hopefully published sometime next year. The other thing that we're working on that'll be coming out next month is an analysis of what we call value deflation of solar in California. Essentially, the idea there is that, you know, solar panel is incredibly cheap, or solar power is incredibly cheap these days. It's the cheapest form of electricity at the margin in many parts of the world and many parts of the US. But the challenge with solar is that, you know, it's only producing electricity at a certain time of day. And at some point, you've got so much solar that getting more solar electricity generation at, you know, 1 p.m. in the afternoon is not very useful. You're already using, you know, the solar already meets almost all your electricity needs. And so California, which is one of the world leaders in installing solar panels, is actually getting pretty close to that point. During certain times of the year, like the spring and the fall, in the middle of the day, we actually have negative electricity prices pretty frequently now, which essentially means we're paying people to use all this extra solar energy that's coming onto the grid. That's not to say that all the solar is useless, right? You know, you might have extra solar at 1 p.m., but you're, you know, really can use the same solar at 4 p.m. in the afternoon. And so what we're doing is we're building a model of the California grid to essentially answer the question of how has the value of solar to the grid changed over time as more and more solar has come online. And so we're finding, you know, that a solar panel installed today is about 1/4 or 25% less valuable than a solar panel installed 5 years ago, because, you know, prices during the time in which solar panels generate have fallen quite a bit. And so that's what we call value deflation. The more of it you have, the less it's worth at the margins. Now that might sound bad. You know, solar is worth 1/4 less today than it was 5 years ago. And it's a real effect, but at the same time, solar has become about 50% cheaper today than it was 5 years ago in California. And so as long as the price of solar follows faster than the value deflation, there's sort of a race between the two, then it still makes sense to install more and more solar. And so there's an interesting question of when does value deflation catch up with falling prices? Because solar prices can't fall forever. You know, there's some what we call soft costs, install costs, for example, that are, you know, much harder to get to very low numbers than simply the cost of manufacturing the panel. And so sort of we're looking into this question in California, both trying to quantify empirically how much value deflation has happened, and then sort of look into the future about how much value deflation might happen as we get more and more solar on the grid, and sort of how that compares with what we expect to happen around falling solar prices and where those two sort of match up.
Great, interesting. Well, I think we're out of time for today. Thank you both so much for joining me. And I would just say to anyone listening or watching, please visit berkeleyearth.org for real-time and historic air pollution and global temperature data, and to keep our work independent. We do rely on your support. So we hope you'll visit our website and make a donation. Thank you very much.